and today designing modern board games based on George Philly's forthcoming book, A Class in Board Game Design, Lecture 14, Gridding. So today I am going to talk about gridding, the notion that if you have a game with a map, in some sense, well, do you break the map into areas in some ways? Is it just going to be nice and pretty like a local road map? And there are various answers to this. The historic answers, if we go back to chess or checkers, is that you break the board into little squares and you put units on the squares. Those of you who have played Risk will have seen a map broken into areas. A few of you will think of Chinese checkers, where effectively the units are the little marbles are placed in the holes, which are linked by lines. Some of you play Go. We established that at the start of the term. And in Go, you place the stones on the intersections. So there are various ways of doing things. I suppose the first question is, why do you want gridding at all? For example, if you have a movement, why don't you say the allowed move is 6 inches and we will break out a ruler and measure? And the answer, of course, is that sometimes it really matters whether a move is legal or not. And so if we say, this will be again one of these war games, we have a cavalry unit here, and its legal move is 6 inches. And to go into combat with the infantry while it's attacking from the rear before the infantry can turn around, the cavalry unit counter the stand on which the horse is sitting must be in contact with or on top of the infantry stand. Well, that means the infantry stand had to be at 5.9 inches from the cavalry at the start of the turn, not 6.02 inches. You may reasonably suppose that as soon as there is a measurement and there is a possibility of disputing the measurement, there will be great altercations and disagreements. Worse, if you're measuring from point A to point B, unless you are very clever and use, for example, measuring pins, and the pins are stuck in the ground at each end, which you could do if you're playing on a sand table or a cork board or something. Once I've moved the unit, its former location isn't stored anywhere. You can't tell where it was, and settling arguments as to whether a move was legal or not may be challenging. So how do we avoid this? And the answer is we use gridding. We break the map into areas, maybe not areas like our carpet where each area is a different shape and size, but areas, and you're allowed to move, say, 6 areas. And gee, people can count 6 areas, and there's no question of how many areas is 6. Let me rephrase that. If you are playing with someone who wants to argue about the value of 6, you are in the wrong game. So coming back to that, so what we do is to say we break maps into areas, and this is how we can be precise on where units are and where they can move. So how do we break things into areas? And the answer is, we'll start with the most familiar choices, and then we'll get more exotic. And one answer is, it's very easy to draw straight lines. And so there are a bunch of straight lines, and here is a chess piece of some sort. And the chess piece is, say, a bishop, meaning it can move. This is a Western chess bishop, not a Chinese chess bishop or the Japanese chess equivalent. By the way, I think I confused the rules of Chinese and Japanese chess last time and apologize, or a time back. Moves like that. 1, 2, 3. And if we advance from this to, say, a traditional board war game, you're going to be seeing some of these later in the term. It may be tank division, it can go 1, 2, 3, 4, 5. You'll sort of have to imagine where the grid squares are. And it has now moved square by square from point A to point B. However, because it's moving square by square, there can be no doubt as to where it started, where it ended, what its path was, and exactly how far it moved. That's why you do gridding. Also, we know where it is at the end. Now, there are choices other than squares. The simplest choice other than squares is old-fashioned bathroom tile. It's little hexagons. I am not sure why there was a fad going back to about 80 or 90 years for bathrooms to be paved in very small hexagons of ceramic tile, but they were. And you would say, well, this looks completely different than squares, doesn't it? And the answer is, well, it does look different, and it has some advantages and some disadvantages, but it's still a grid. However, the hexagon grid has one feature that the square grid does not. Here is our square grid. And I said, if we're talking about a chess game, we play on the square. However, if we are talking about Go, you play on the intersections. But if I look at the intersections as a lattice of points, it's 19 by 19 points. If I instead said I have this alleged Go board, which was redesigned by some Western barbarian, and it's 19 squares by 19 squares, and now you play on the squares rather than the intersections, it's still 19 by 19 in a square. It's exactly the same game. Nothing has changed, just you're using the intersections or the spaces. The squares and the intersections are what are called a lattice, meaning it's sort of lined up crisscross in some sense, and the dual lattice, but for squares they're the same. Consider, on the other hand, hexagons. I mean, each hexagon obviously has 1, 2, 3, 4, 5, 6 nearest neighbors, just as each square has 4. But contemplate the vertices on a hexagon. Each vertex has how many neighbors?
3.
3. And so the lattice of vertex points on a hexagon board is completely different than the lattice of the original hexagons. And so you have a lattice and a dual lattice, and they're really quite different. Now, there's another way you can completely dissect a plane by using a regular, simple-minded, completely regular geometric shape. And that's the equilateral triangle. Of course, you have to be a little creative on how you do it. And if you look carefully, you will notice this is a complete tiling. That's the magic word. Tiling of the plane. Tiling is the word the mathematicians use into triangles. Now you might say, gee, triangles look a little funny. I mean, if I used a triangular shaped playing piece, when I move it to the next square, well, the next triangle, it's got to be facing a different way. Okay, so you want to make the playing piece small enough so that it will continue to fit if you move it over. However, are triangles really new? Let me point out something. Each triangle has 3 neighbors. However, if you look hard, So this triangle has 1, 2, 3 nearest neighbors. This triangle has 1, 2, 3 nearest neighbors. The triangle down here I didn't draw in has 1, 2, 3 nearest neighbors. So does this one and this one. And you may notice this suddenly starts to resemble hexagons, doesn't it? And what has just happened, the tiling of triangles is in fact the same in its connectivity as using hexagons and playing on the vertices. Now, the ancient Greeks sort of concluded that this was all of the possible ways using regular geometric convex shapes to tile the plane. It is, however, possible to be considerably more imaginative. And in fact, if you don't insist that they be regular, you can, I'm not going to try drawing it. You can find it on the web, though. You can find it on the book I sent you. You can tile a plane entirely in pentagons. And the pentagon, it's not a all 5 sides equal pentagon. It's a sort of distorted pentagon like this. And you have to be a little creative on how you bring them together and how you draw them, which is why I said go look in the book. I'm not up to this. But you can tile the plane in pentagons. In fact, there are 14 known different tilings of the plane in pentagons using pentagons that are convex objects. Of course, if you say, let's draw a pentagon like that, if you start using really weird shapes, you can get all sorts of things. But if you say, let's use regular pentagons that just look squished a bit relative to what you were shown in grade school, is the pentagon, G, you can tile the plane in pentagons. Once upon a time, while I was alive, there was an English mathematician by the name of Penrose. And Penrose invented a way to tile the plane using 2 shapes, which I will attempt to draw not very well. And they're both sort of like this. They're both squarish, but they're very differently shaped. And they have the feature that if they will pack together completely regularly. There's some rules to follow in putting new ones down so you don't tile, so to speak, tile yourself into a corner you can't get out of. And the Penrose lattice has the interesting feature that if you look at all of the boundaries between the sides, they lie on a very small number of lines, and the Penrose lattice has 5-fold orientational order. Orientational order means that if I ask the principal directions, the directions defined by the sides of the shapes, there are only 5 in Penrose, it's actually 10 principal directions. And so the Penrose tiling has orientational order. It's not random. All of the sides are parallel to at least some axis, just as for the square, all of the sides were parallel to due east or due north. However, the Penrose tiling has a feature. And the Penrose tiling has the feature that while it has long-range orientational order, meaning if I create a huge Penrose tiling out to Institute Pond, and you measure the directions of the tiles, they're all parallel with each other, and up to, it's a mechanical engineering object, and flexes a bit. Over infinite distances, all of those directions are preserved, but there is no repetition. That is, if I say we have a square lattice, square, same, there's the repetition distance. If I do the equilateral triangles, there is the repeat unit. And the next two equilateral triangles repeat because it repeats. This is called translational order. The Penrose tiling has no long-range translational order. If you look for a repeat structure, it's like looking at bathroom tile in a large women's room or men's room where the guy laying it down has gotten fancy, but if you look carefully, you notice every 3 feet it's the same pattern. That's a repeat pattern. The Penrose tiling will go on forever without repeating. Unfortunately, Penrose was a very clever fellow and patented its use for game purposes, but there are a number of things that are not Penrose tilings that are similar. The most amusing of these, in a certain sense, is called dragon tiling. Well, it does look, the individual spaces look vaguely like a dragon that has been passed through a fractalization ray, so it's got lots of weird spines and shapes sticking off. There's only one dragon shape, and the dragon can be used to tile the plane. It is a little dismaying to look at because you have this humongously complicated shape. But Mr. Humongously complicated shape, if packed together the right way, you can just keep going forever. However, suppose you look hard at the dragon tiling and you ask one question: how many neighbors does each of these dragons have? How many next door neighbors does each of these shapes have? And the answer is 6. Or if you prefer, because there's a question of what adjacent means at one point, 5. And so it's in fact a very odd way to draw a hexagonal or perhaps pentagonal lattice. So this is the notion of tiling. You can split things into shapes, and because you've split things into shapes, you can regularize the map. Well, that's very nice. There are a few things, however, that you can do if you're a little more creative. Here's the square, and I mentioned chess, Go. However, there's no reason why you couldn't also allow counters to be placed on the edges. In fact, let me give a thought on this. Think back to brass. We put all of the nice, pretty cities on squares, and the function of the canal counters is to sit on the edges and link squares together. And so we would have actually city stuff, canal or railroad stuff, and so on and so forth. So are we sort of good on here are ways to tile? There are, however, some alternatives. One alternative, which you have already seen, or about to play since the next game for the rest of the lab, is Conquest of the Fallen Lands. And the alternative is an area map. So there is an area map, and the terrain is split into blobs. Now, if you're actually doing an area map, this has the limitation. You actually have to draw each of these areas individually. In contrast, as at least one of you has discovered, if you simply want to split an area into vast numbers of hexagons, you can download the vast numbers of hexagons from the internet and then draw your map on top of the vast numbers of hexagons. And if you have simple geometric shapes, squares, triangles, funny pentagons, hexagons, these shapes can be done computationally. This has been true since the first hex paper was drawn using a CalComp plotter program and a program written in Snowball, a language so old that it went out of date before most of your parents met each other. Yeah, that's true. And run on an IBM, you don't want to know. In any event, if you're doing areas, you kind of have to do it by hand, and that's very time consuming. But if you're clever, you can get very good areas. There is one little issue you should realize, though. Here are 4 objects. I could have inserted more, and they appear to meet in a point. And the question is, what is the movement rule across the point? Well, if you're playing some things that move on squares, here's a bishop's move, and moving diagonally is allowed. And if you're playing board war games, the answer is that you will have to be told whether diagonal moves are allowed or forbidden. But if you're drawing an area map, as a general statement, you want to avoid complications like that, and so you avoid drawing things as 4 corners unless you really, really want to. It's something you don't want to do accidentally, and now that map works rather better. So this is an area map, and the point of area is area control. Well, if you're going to have area control, one piece of color is nice, pretty areas that you can be controlling. These are nice, pretty areas that are not like London of the period of brass, when it was ridden with a certain amount of smog. And when the smog got bad, vast numbers of people died. So here is an area map. Now let's consider the equivalent of an area map done for a Go board where you play on intersections. And the Go board, of course, you have intersections, and they're connected by lines to show connectivity. But you could imagine a road map. So here's Worcester, and here is Holden, and here is West Boylston, and Boylston, and Shrewsbury, and Auburn, and Paxton, and Leicester. And I am sure you are getting the idea that I don't actually have to go through the vast list. And from some of these places, there are roads that take you from one to the other. And if you go out here at a distance, you discover there are roads, but if you want to get anywhere, you have to go around in a circle a bit, because there's this nice, pretty reservoir out here, which, if you are into hiking or biking, some people are fond of going around. It's smaller than the Quabbin Reservoir. It's larger than Lake Quinsigamond, I think. So here is a reservoir, and gee, those roads are connectivity points. And say, so what you've said is, we have an area control. You're going to control towns, but movement is point to point, and so we will just show the roads. This is the same as the octagon Worcester, and here are various towns facing off on various sides. You could draw it as an area map more irregularly. The alternative is we will represent the towns as circles, and we represent the connectivity as lines. Now, of course, once you've said you have a line or an edge, it doesn't have to be a featureless edge. We have a game on Girl Scouts rescuing people from a crashed airplane in an area where helicopter transport is impossible. I'm sure you guys can come up with something more creative. You might say, here are the areas, and some of them are just plain terrain, 1 point to cross, and some of them are fairly irregular, 2 points to cross, and some of them are really bad terrain, 4 points to cross. And then, of course, this is one of the walls of the Grand Canyon, isn't it? Infinity to cross, you really have to go around or do it in stages. When the first American explorer found the Grand Canyon, they looked, it's a deep valley. and there was what appeared to be a passable path on foot or by mule. And they said, okay guys, several of you go down there and we'll have a good baseline and we can see how many 100 feet deep this is. And they waited, and instead of it taking an hour to get to the bottom, it took several days. Then they realized the Grand Canyon is a little bit bigger than Institute Pond. So in any event, you could mark crossings, and if we are doing this as dots connected by roads, you can mark, and you can therefore indicate passage costs that do not have to be uniform. So you have a map and you have gridding. Now, I'm not going to go for the full hour because there is the lab game. The last bit on maps that is of substantial importance, if you're drawing a map, sometimes you want to indicate terrain. Now, sometimes the terrain is purely colorful, and therefore, here is a sea area, and it's like the map on the cover of one of my books. If you look very carefully, you will note in one sea area there is a sea monster. And if you look even more carefully in another area, you will notice that there are several swimmers and several sharks and perhaps hot pursuit. Well, those aren't terrain features that affect the play of the game. They're just decorative. Nonetheless, they're terrain features. On the other hand, you might say we are doing a game and we are going to indicate terrain features that matter. For example, if you are building a railroad, it is one thing to be building a railroad across the Great Plains or outer Mongolia or the Ukraine or someplace that is really extremely flat. On the other hand, as soon as you hit hills, the cost of building railroads goes up a lot. The cost of building canals becomes astonishing, though it's a solved problem. And when you hit mountains, things get really bad indeed. There were several solutions to canals hitting rough terrain. One of them is locks. So you raise and lower the boat up a series of locks. These work better if you aren't going too far and if you have a huge supply of available water at the top, because every time you empty a lock, you've lost the water. The other choice, which was done with canal boats, was you load the canal boat onto a really big dolly, and it's a canal railway, and the canal boat is hoisted up to the top, lowered back on the far side, and the canal boat has moved a short distance by rail. Expensive. So, traditional map symbols. I'll do this with hexagons. And plain terrain you don't have to say much with. Swamps, it's water, it's reeds sticking out of the edge of Institute Pond. You could also have hills. And hills, well, one traditional solution is hash marks like this. Another solution is, if you really have mountains, if you're going to indicate a city, well, the simplest indication of a city is, that's the road net, isn't it? And the roads are the colored lines that come out of the city and go off. The railroads show the railroad ties. So there's a railroad, there's a road, there's a city. Further alternative, there are a couple of variations on this, but they vaguely look like trees. Or if you don't want to draw a lot of trees and you want to be sure that it's simple for the artist, you simply shade in some color like green, and people work out it's trees, a forest. There are vast numbers of terrain symbols out there. If you ever need a really thorough set of terrain symbols, the best place to go that I have found are civil aviation guides. Because if you are giving a map that would be used by someone in a small airplane, you want to show as much as possible. I have gone up in a small plane a few times, and I'm alive afterwards. And the important issue is you can't read road signs from up there. And one of the early lessons in piloting is to warn you, there are real idiots whose idea of navigating in a private plane is to follow the interstate. And they are paying attention to the interstate, not the airspace through which they are flying, in particular the airspace that you are occupying. So you follow the interstate is not a good idea. And so you show all sorts of things that would be visible from the air in daylight or in darkness, and it's amazing what there could be. And because you do this, you need all the map symbols for it. And so that's what they do. Okay, I have said a great deal about map symbols. One could go on at vastly more length. I could say much more about gridding. The main thing I want to get across is that if you are going to grid, yes, area maps, like in Conquest of the Fallen Lands, are good. It is area in a very peculiar sense now, isn't it? And real area maps, like in Risk, are certainly very nice. Grids, chess, checkers, Go, are very nice. But there is a lot of opportunity to be creative in ways that are simply not hard for the poor players to remember. It's very important if you're designing a game not to give them rules that are incredibly hard to remember, because if you get the reputation, it's a neat game once you've spent 2 weeks learning the rules, your market may be a bit more limited. In any event, I have said what I want to say about map gridding, and so we will bring this lecture to an end.